Uh, basically, I'm trying to introduce the Open Sense initiative now. I hope I don't lose this video. I already started it. Basically, 1 second, guys. Let me just give my free cam. Look. Basically, I'm just in Thorok right now. Look, Thorok, change.orgs slash underscore OBINexus reform. Look, I'm not joking, guys. £36 million into my crypto wallet. I'm leaving UK. I'm tired of space. I don't want to be here. It's a free of charge. The Nigerian passport. You don't have to pay for me. I got my passport here. I can show you guys here on my passport. I can show you everything on my passport. Don't care. I'm not Nigerian. I'm a BFM. So basically, I found actually 205 for you, Torok. You know this, Torok. My heart is not for you. Basically, bitch, I just infer the symbol, guys. It's kind of funny because if I infer the symbol, it flips all the way, and it's like Nexus Obi, Nexus Heart, because I don't understand them. Anyway, it got it wrong this time. Oh, I can flip it now. Actually, let me just try to do it. Uh, so don't worry about it. So basically, the term saying to you guys, Torok has to pay this money. They have to pay this money. So this is my diagram here. This is called the noise diagram. This is open signal initiative. So you see here, this is obviously in our dimension epsilon. E stands for epsilon. E stands for epsilon again. So if you go right to our dimension, you get add plus. If you go to negative to plus, you get epsilon. Add this, you get numbers. You get 1, 0. This is a model basically. It's like, the smallest units of stuff. What happens accumulates becomes something. From nothing in our universe. So basically, you get two types of nothing. You get like the dimension x nothing. See, E for epsilon. Oh no, please let me record this correctly. I basically need to get a transcript from this really. So you get two kind of states. So you get so you get two kind of states here now. So basically, I'm trying to get to my exploit again. So see this. So you get the x, the y, the first x coordinate, the x1, because you got like dual state heterogeneous states. So the negative epsilon, basically it's a plus negative property. So this one is plus negative. So you have to get it right, guys. Plus to x and plus to plus. So basically, the plus model is like, if I'm in my dimension, this connection, the polarity, this is something called polarity. So polarity is very important to understand polarity in anything you do in quantum physics. So you get like a plus to negative. So plus, so basically, if I add numbers, 1 plus 2 is 2, but that's 2 positive numbers. So if I add 1 plus 2 is 3. Let's just start. 1 plus 2 is 3. Now, if I do 1 plus minus 3, that I mean the 3 minus 3 takes precedence. So 1 plus 2, 1 plus 2 equals 3. So what would that be? 1 plus minus 2. 1 plus minus 2. 1 plus minus 2 equals what? 1 minus 1 is 0 equals minus 1. So you get 3 here and minus 1 here for 1 plus minus 2. But it sounds kind of weird how I do it. Because I'm trying to give you some example how I'm doing this. These are called conjugate pairs. So this is a model. They're based on homogeneous and heterogeneous conjugated pairs for the y-axis and the x-axis respectively. So you're gonna understand the takeaway of this. So if I did just unit scalar, the smallest thing you operate on in your reality, ontological reality. So in my reality, I have 1 plus 2, 3. Now I get 1 minus plus 3. So if I have a minus, the minus is present, that'll be 1 minus 3. 1 minus 3. And that'll be what? Minus 0, 1, 0, minus 1. So that'll be minus 1 or minus 1. And that'll be the units models of minus to plus, and then the last one goes minus to minus, minus to minus. If the thing takes you're subtracting all dimensions. So the canonical position for minus to minus is 1 minus square equals to plus. So you get 1 plus 3, 1 minus equals to plus. So therefore you get 1 minus 2 equals 3. And that means 1 plus 2, 1 plus 2 equals 3 in all dimensions. So 1 plus 2, 2 equals 3. So the idea of this is just to give you the small overview. Let me give it again. So here I've got an encoding table for this. because the inhibitors were bound to it. I don't want to encode it yet, because I plan to do other things today. But I'm hacking. I'm trying to hack Thorough. I don't really care. I've said it because for me, in my framework, there's no hacking. It's just their collection. So I will try to fight the force. That's the accident for to file my bankruptcy, so I can get 360 million pounds axed by phone call, which is kind of funny. Which they filed in code section 205 to them. So let's go to the bare minimum. So the encoder table is for the output is 1 plus 2. 1 plus 2 equals 3. 1 minus 2. 1 minus 2 equals minus 1. 1. What should I do now actually? Because I have all day. 1 plus minus 2 equals 1 minus 1. 1 plus 2 minus 2 equals, because there's an order to it, there's an order of operand. What? So 1 minus the plus, basically you get plus to plus, and you get 1 minus 2. Wait, sorry, okay, we're gonna do this. I'm trying to clear the table. 1 minus 3. 1 minus plus 3 is what? So minus plus 3, 1 minus 3. That's basically 1 minus 3 equals minus 1, 0, minus 1 minus 2 equals minus 2. And 1 plus 2 equals 3. So minus 1 minus 3 minus 3 equals plus 3. So that's plus. That's you get an encoded sum of 3. In my reality, plus in my reality I get some kind of pair conjugate. So the result for me in my reality, I'm trying to measure this correctly now. If I fuck it up, so in my reality, if I see 1 plus 2, and it's all positive, I get all positive operators. Using my system, like positrons, like in the y coordinates, like polarized this direction, or sparsely polarized this direction, in that direction, not order, from the 0 or 45. Basically, if I get 45 degrees up, I'm going infinitely, but anywhere between my 90-degree range, that's plus minus 90. Wait, sorry, minus 90. So 90 clockwise, counterclockwise. Measurement. So 90, 0, 0. Because you have to think about the polarity too. For the last, let me try to calculate this properly, Namdi. So if I do it wrong, I fuck this up, and someone will blame me. You messed up your calculation. This guy died. Now you have to take you to interdimensional code. Because they definitely do have. What am I saying? It's infinite. So try to use calculus of our infinite structures. So using lattice system. So lattice system. So basically this is an x-dimensional. This is for x-axis because it's 2 dimensions a minimum you need. But you have a total of 3 dimensions you can operate on. Because it doesn't really matter how you encode it. It's more of the alignment of intent. For example, let me do it properly. So because I'm trying to calculate game. So I'm trying to basically I'm going to our number theory, our foundation number theory. I'm not even thinking about numbers like I didn't want it to. I'm not thinking about that. I'm thinking about number theory. 1 plus 2, 2 equals 3. This is our reality. 1 plus 2 equals 3. So when I get to 3 in my reality, my universe, who I am, where I am currently, I expect someone in the opposite universe on the opposite spectrum. Where they have a electron, where electron is a positron, where electron charges are positive, so they use a positron to charge their stuff, and the electron has to get, basically the electron have to have negative energy, have negative mass, to go through the system of channel. One more thing. So if the electron has to have negative mass, the positron has to have negative mass. He has to basically our world we have positive mass, we have things that are positive in mass, but electron has a positive charge. So a positron will have what, a negative charge, and vice versa. So you gotta have understand the realm. So you got the electron dynamic. An electron for every electron in our universe is an equivalent and conjugate pair, equivalent in mass, size, and in force, force mass, force equals mass concentration. Force equals basically Newton's principle for quantum system duality. So you get the Newton's ones. Force equals mass concentration, and then you get so in our reality, force equals mass concentration. In their reality, from their first from for their pointer, they're seeing they're gonna see that this is something you have to decode intercept. So the force equals mass concentration is not just okay. Net force equals 0, and net force equals 0, and what else in our reality? The canicality of this is here. So and then force equals negative force. See this one? This is just this is the bare minimum. It doesn't reach the full degree of what I'm going to explain next. So where do I go here? So it's just basically unimodels for canicality. If you're building a polyglot something, you're gonna understand this is why I'm trying to do this way and just not go into it by force, because I understand what I'm doing here, guys. So basically, in my reality, we got a force equals mass acceleration. But we can have a negative force in our reality. So we can have two force, negative force. For negative force equals force. But we have to have the combination of that key pair to give it. So for every negative force, there's a negative force in our reality. We can counter in our reality only in our space time. So if I punch myself, I feel the force. I get negative force there. I feel the hurt. If I then punch my fist, I get sponge. I get like a little fist bump going, and it's all equilibrium, all equality. So here we get a peace sign. Get onto peace sign. Basically Nexus OB can flip it. So if I mean Nexus OB, this evil, basically Nexus OB, and this other guy. That's me. So negative force or positive force have the unconjugate pairs. So that must mean negative force plus negative negative positive or positive or negative. You get negative force, negative positive force. Sorry, force. You get positive to negative force, and you get what? Positive force. So the canicality system of the matrix for the X gate, because if I'm basically operating on the X lattice, the lattice, X lattice, I have to just use this one system, based on Newton's credo. But Newton's laws really apply here. So the invariant Newton credo. So I'm trying to define this properly now. So net force equals 0. Net force equals 0. That's the canicality principle. So if I want to model this problem, net force. So net force equals 0. What would that mean in our reality? In our reality, that means first of all, net means 0. The sum of objects, the sum of force is equal. It's like a uniform. It's uniform distributed. That's like what gravity does. So you get some kind of no effect. You don't feel it. You just know. You don't even know it's there. You can't. You may even be able to measure it. Based on what you observe, what you see, because for the system to all balance itself, for this to be not the case, there has to be some kind of entropy that keeps them balanced, and that's what the net force is in our universe. For example, gravity, we don't feel the effect of gravity pulling us down and hurting us. We don't feel like cancer cells, cancer radiation. We don't feel gamma rays until it's too late. Those things like that, we don't measure that with our visible eyes. But it is there, and it does propagate in a kind of in our system environment. So the canicality is like what is the net force of 0, 0? The net of 0, 0 is epsilon. Epsilon. So epsilon force. So to have no force, you have to have what? No energy, no mass, no signal. So this is what I'm saying. The signal initiative. The first signal initiative. Let me go here. Is basically my legislation, and my legislation conceived to council. So this is my legislation, ontological polarity. Basically, it's about polarity. My system. So I will not become what to break me. So basically, what I'm saying to you is the polarity concept is I have to polarize X, Y, and Z in my lattice space. But every rift art syntax must have F, S, Y, and Z gates, a minimum. But the gates have dimensions, so dimensions are really what it's all about. For basically the basically you have a total of nine dimensions you can operate on and work on in real time. Open signal, so bound. So one thing to signal processing framework for authentic communication signal. So you get signal. That means you understand information you're getting from the cross-dimensional bridge. Uh, but if you go to the four ones, you get four types minimal you can operate on. Open uh, open sense no signal. So you get no signal. So that means like everyone agrees there's no signal here. So it's all about what I'm in university A, university B. But no signal is just like the canonical representation of it. So I'll start here. So what it means to have an information in our system, in our world. So in our world, we have a net force, the stream of currents flowing through a wire. The current is electron bound. Electron bound. So if you got a wire, electrical cable here right now, you have electrons that get excited, but they don't get excited in tropospheric extent. They don't like you guys. They get polarized in one direction in our universe. They get polarized. So the polarity in our universe is they have to they negative. They're positive. They're negative naturally. The iota states, I call it. Iota is negative. So in our universe, electron is just you cannot change the static state of an iota state. That's for sure. But you know, in other universe, the inverse of an electron is a positron. A positron. So that's what I'm saying here. So for something for force to happen in a wire, for current to pass, a voltage equals current equals voltage times I. Current equals what's current? Basically, let me try to find work out what is current. Let me try to work out what's current in our universe. The current formula. So basically, it's very important you understand this formula right now. Current calculator, math. It's fun. So basically, I'm trying to calculate the current in a wire. Basically, you have to have like four cases. Calculate a current. Uh, math is fun. This is a current time. Basically, I'm going to try to calculate this properly. Basically, the charge of a current is a current times time. The charge, the electric charge. So, the electrical is defined by how much charge you transfer per second. Therefore, current equals change of current in a y equals a charge over the time. So the symbol for charge is Q. It's measured by the Columbus. See, so the symbol for current is I. I need to piss, guys. Guys, let me piss first. I'll be back. Oh, okay, I'm back, guys. I just so one thing to you guys, it's very important. Understand this very well because you know if you make a mistake, you will not be able to gain the correct information. So, let me give you a sample problem. Let me try to do it now. This is to start itself, like dictate. Sorry guys, 1 second. Okay, no. It has to start again. Okay, so so basically the problem trying to formalize is this. You got the representation of the system in two forms. But you know you have to have the something called a polarization. Basically, you have like a four encoding table minimum. basically, I'm thinking of a try. Basically, wait 1 second. Basically, what's my? Oh, so basically, I'm trying to find the problem I just saw. I just lost it. Is it matter form, guys? I don't really see it here. So basically, yes. So basically, you have like a four state you can be in. Sorry. So you get like a current going through a wire, properly. So let me give you the properly. Basically, the paper I'm using is kind of like to yeah. So you have like a so basically you have like a the current going through wire. So basically the current is the current equals charge over time. But the current is the symbol for charge is Q. So Q is measuring Columbus. So if Q the charge and C the Q charge and then C Q the measurement of Columbus equals C. But you know it's a C. So Columbus. I don't like the Columbus unit. I just like the system being polarized. So the Q is what charge, and the Columbus is the measurement of the charge. Uh, but and you get the symbol for current is I, and measured in amperes A. So you get the symbols for T is time. You get seconds, time, second, second. So vice versa. So Q equals I times T. That is what is called the charge. So calculate the charge that passes through a lamp 2 minutes if in 1.5 amperes. So basically, 2 minutes is basically the charge will be so if the Q is 1.5 times 2, that'll be 1.5 is what the charge is 1.58 amperes. That's the charge. The charge is in 1.5 amperes. So the charge is 1.5 amperes. Therefore, the current is what? The current is I 1.5. So the charge is so the time is now 2 point wait 1.5 times in basically 2 minutes. 2 minutes is what 2 minutes is 60 2 minutes. Basically, you got 2 minutes. So 1 minute is 66,000. Is it 60? Is it 60,000 nanoseconds? Milliseconds? No, no, no. Basically, you have 60, I think you have up to 1 minute is 60,000 seconds. No, 30,000 is half a minute. So basically, I assume no 60,000 seconds is 60,000 seconds is 1 minute. Then 6 seconds, so 60,000 seconds is 1 minute. Therefore, this is fine. But basically in the same thing for the milliseconds, that'd be 60,000, 600 seconds, 60,000. Because it's not 600 because it goes up in double force. 2 units at a time for the nanoseconds because you divide by 10. So 60 divided by 10 is 6, 0.6. But this is the 10. Wait, 60 divided basically a millisecond is a millimeter long. A nanosecond is millimeter. So it is 0.6 because it's 10 shorter. So that's 0.6. But the nanoseconds is 0.06 seconds. 0.06. Okay, so that'd be 906. So that'd be divided by 100. That'd be unit model. So basically, I'm telling you guys the unit model for time in this framework is 0.6 seconds. But that's the unit model. That's just the x one, and then you get the unit, the like the fractional unit of it, and then you get what the tens, which is 0.6, and you get what the fractional units, and then the tens, and then you get the 100, which is the 6 seconds. The time 60 seconds is the seconds. Seconds, but this will be 6 seconds. This will be 60 seconds equals 60 seconds equals 1 minute. So that's 1 minute and a time. So in this answer, we get 1.5 ampere I for current. I for current equals 60 seconds. Now 60 times 1.5 is what? 5 1 0. Okay, 1. So 5. You can put the 5 down. 5 you come down, so you get 5 times 6. 5 times 6 is 20. 21, 22. 5 times 6 is 20 because nothing else. And you get 20.5. 1. You get 0 plus 0 times 1 is 0. 1 times 0. 1 times 6 is 6. And then you get the 1 down. And then you get sorry. Let me just do use your calculator. 60 times 1.5. Wait. So 60 times 2 will be what? So basically, I'm thinking of basically every 2 minutes that will be 120 seconds. 120 seconds is 120. So every 2 minutes the current charges through the lamp 2 minutes, 120 seconds. But you can use this properly. So you have to have 3 minimum. So you have basically I'm trying to give you my take on it. I'm not even talking about what's in there. On what I'm watching right now. I'm giving you my take. Guys, give you my take on it. So I'm making a quantitative breakthroughs here. So in the unit framework, I have in nanoseconds have 0.06. In nanoseconds and then nanoseconds and then in milliseconds I have .6 milliseconds and then I have 60 and then wait, basically I have 6. No. I have basically I have no. Oh, basically I have no. I'm going wrong. So you got 60 seconds to a minute equals a minute. So that means 6 seconds equals one entire minute, 1 entire nanoseconds, one entire milliseconds. Milliseconds. You divide the other. You keep them and you keep them. And you get 0.6 nanoseconds equals nanoseconds equals it's just a fraction of a second. So you get a fraction of a second. 1/4 of a second is 0.6 nanoseconds. 1/2 of a second is basically you half it. The half row. You half it, half of a second, but half means 50%. So 50%, wait. So you divide by dimension. So basically, I'm not thinking. Basically, you get a quarter of like you get a nanosecond 0.6, 0.06 seconds. The nanoseconds 0.6. Wait. Oh no. Oh yes. Basically, yes. I'm right. So basically, nanoseconds, milliseconds, and seconds are some because they're also seconds. So you just have to pick what you want. So if you want to calculate the nano ones, that's nano means 1,000. Nanometer, nanoscale, nanite. So this is like what you see in cells, nanoid, nanite, some kind of anti-nanoid, the things that connect 0. 0.6, 0.06. Basically, you can use this as a unit model. So you get something called a scientific number. So you get minus 2.6 minus 0.26 0.6. Basically, scientific form you have like something called basically I'm trying to create some called guys. So you get 0.26 0.2 squared. So you get something called 6 to 0 squared. So you get 0.206. And then you get 0.06, basically you get some kind of fractional scaling because of this that grows all the time based on some threshold model you're using. For example, okay. So basically, I'm trying to put this now, bound by rules by it. So you get 0.6. 0.06, that's the 0 or dot fractional units, fraction. Basically, you get like an FU. Give me a second. FU, F10, F1000, F100, and then etc. F1000. And basically, that's the one I'm using. So the F unit is after the dot. So that's the dot. So this one will be 0. The unit one was 0.06 to fractional, and then you get the unit, and it's like the nano, like 100. No, 100. Basically, this is a 100 term. No, this is a tenth, 100, 100 tenth, 100 tenth, tenth, 100 tenth, tenth of 100, tenth of 100, guys, tenth of 100, and you get this. So you get 0.6 for the milliseconds. Milliseconds you get 0.6. And once again, guys, and you get 6. No, that's not right. So if this is 60 seconds equals 1 minute. No, 60 nanoseconds. No, 60 seconds. No, 60. No, wait, I'm thinking of this properly, guys. 60 seconds. 60 nano, milli, and what? 60 milliseconds. Oh, yes, 60 seconds. So this is a, then you have 0, you get no nothing here. So if this comes here, it comes 6 seconds. So this is this nano, this is milli, 6, and you get 60. 60. So basically, including like a quarter, this is like 60 seconds, and this is a minute. This is a minute. So basically, guys, I'm trying to give you guys the audio. So basically, see this table here? You can see the conjugate pairs here. You can see 60 0006 0.0 is units. So I'm estimating that this one 60 seconds. I'm not estimating. Basically, it's like a dynamic scale system. Basically, it's a measure. It's not static because if my scale breaks, I'm not getting anything. So this one making a policy to do it properly. It's called a dynamic scale. So you can measure the right things properly based on what you observe. So if you are measuring 6 seconds, you get 60 seconds. Like, get 60 milliseconds. And you get 60, wait, that's milli means millions. Oh, no, I'm getting it wrong. So you get 60 units, you get like 60 seconds equals 1 unit, 60 milliseconds, millimeter unit, which should be on the right, in a 60 million is on the left, and then you get the 6.6 seconds, get a unit of it. So that divide. Basically, you get I'm trying to get it. So you get nanos. You get like a. I believe this is. I'm gonna do this right thing. Yeah, this is not a nanosecond. This is like a millisecond. Million, minute. Yes, millimeter second, because for minutes, minute to second, scalar, and you get second to second here. Second, you get a minute to second, you get seconds to what? Go up, you get seconds to nanoseconds. Nano to milli. So you get nano. So this one's nanoseconds to what? Seconds to up. So this is a seconds is 0.6 seconds. This is a nano unit. So if this is a millimeter, this is a nanomillimeter. This is like a unit model. So the unit model is going to be units unit bound only. So you get up. So you get millimeter at the bottom. 60 seconds equals 1 minute. 6 seconds is a fraction of it, which is a half of. It's like a third, which is like a 10% of it. So 10% scale. And you go up again. That's 100% here relative to that millimeter. But what goes on after a millimeter? You get a millimeter. Guess what? So you get like a millimeter, then you get a nanometer. But nanometer is not it's not 100. So our system is wrong. Basically, yes, I think the 60 milliliters is a second. So millimeters, you get millimeters, nanometers, meters of what? Miles. You get basically you have to use the ones. The one you have to kind of use canonical representation for that system in it. Whether it's a size like a force, a size like kilo, a kilometer, kilo means 1,000. 1000k, or milli means 100. Oh yes, I'm doing it wrong now. I got it now, guys. So milli means 100. So this is not a scale. So you get a nanometer, a small fraction of that meter. So nano is a small scale inverse. So you get nanometer. So you get basically you got 60. Guys, I'm again. So you get basically this some kind of naming convention you use in science to do it properly. Let me just try to find my dictionary. It should be here. Sorry, this is like 11 figures of books, guys. Basically, should get it quickly. Should be here, NMD. Didn't write on this. Here, NMD. Didn't write on this. But this is one unit terminology here. Oh yes. I don't keep it into this. So resistance in parallel. The mass of an electron. I didn't write anything down. So basically, this I'm saying, this one you have to keep in the track of. So this is the like recent information for this is like a resistance, the resistance in parallel. So the resistance in parallel are half and half. Like the resistance gets what the resistance of a circuit, like in parallel, that works in a basically series of operation. But you know, that's what I'm saying. So I'm basically it's my policy now to have a dynamic scale based on the unit model, because dynamic scales can learn new information as the project grows. Because you know each one is static, that means it's perfect. But you know there's no perfect system in my view, because I haven't proved that. We can't have a system for this universe, but we have to ensure that the polarity is already there. We're polarizing ourselves correctly and pushing ourselves to the right people in the right way, which is why I'm not seeing this a policy there. So the thing about the dynamic system, it has to remain coherent, unless or holding full. So you should be really static scales. You know, it has to behave like a real thermotic system, thermodynamic system that measures entropy actively and knows what it's doing without actually deviating from our predicted results, and it's and what we're trying to measure in the other person's which is tripartite system. So back to this question. The electron in their world is a positron. So therefore, there's a conjugate pair. For each electron, we have there's a time. So basically, the charge is the time taken. So the current time is what? The current time. The current. So basically, I'm trying to work out the current. The current is what uh, I'm trying to work out for. So let me frame the question. The current is what? 20 let's say the time let's have to fill the formula. So basically if charge equals current times time in my universe, therefore the time the current is what makes the current subject. C is its current after polarizing current correctly. So I have to get the current. So the current in my view is this in this dimension. The current is I'll give the current of some absurd number 50 50 60 what's the standard current side? Okay, voltage current. The voltage is changed 60 30 30 30 30 I is the current currently flowing a wire, and it's flowing at the rate of 0. At in 1 minute's time. I'll do it to 1.5 minutes time, 1.5 minutes time, 1.5. It's flowing between half obviously. If I do 30 seconds, if I do for every 30 seconds, wait, for every basically there's 25 currents moving through 15 seconds. Every 15 seconds. What's the charge? The charge to that. So if I give that question 25 amperes, what is the amperes? The amperes would be 25 times let's just say a unit like half of the time is one unit, so one fractional unit of that. So that would be two. Let's say it's two fractional units. That means 60 seconds divided by 100 times 2. Divided by 100 will be the 100 units. That would be the milliseconds. No, that'd be no millions millions. So 100 seconds 0.6. Let's not do that actually. Let me not confuse this. Basically, I'm trying to write this. So basically, if you've got scientific notation, times 0.6 times 0.6, that'd be 5 times 6 is 30. 6 times 5 is 6 times 6 times 5 times 6 is 30. Carry the 3. 6 times 5 is 10. 10, 11, 12, 13. 150. 150 milliseconds. 160 the unit model, which I believe is 100. 100 current. 100 current. 100 amperes is going through. 100 amperes is going through. 150 amperes is going through every 0.6 seconds. Every 0.6 seconds. That is 150 amperes. And vice versa. So that's the current to wire diagram. But you know, in my model, I have to think about the sparse structure. So in the model of this, I just get one way to do it, and the sparsity of this thing is based on encoding states. So I have to ensure that the rule is correct and is self-correcting Bayesian code. So I'll try to do that with you guys, because I didn't plan to do this, guys. I plan to do something else on here on my desk. But you know, 115 amperes is just the standard current going through this. If the time now going through the charge of 0. 0.6 milliseconds. 150 amperes to 0 is the same as it's going to 0.6 the current. Which is the unit model of 150 125 amperes times 0.6 based on parallel resistors. But you know, basically, this can be in parallel. That means they can split both ways, or in a concurrent. So if you remember resistance is 1/R or R. But you know, if you have the system here, so if 1/R is like where the R is resistance, where R small r is resistance, you get 1/R big R in a parallel circuit. Infinite series of streams. This is not only good enough for like sequences that are coherent, that you can recover quickly. 1/big R one. This is like a resistance in parallel. But resistance is just it's meant to slow down the current. It's not resistance like anything that stops the. It's never like it's kind of funny because the resistance you have to get a resistor to split it off. You have to get because you can't stop a force moving. It is moving, so you have to get a resistor to like slow it down. Also, but the resistors when you have to go in parallel, like the parallel circuit, you have to ensure that the resistance is properly done. So this is a parallel circuit. This is not a parallel circuit here. This is a concurrent circuit. Now, what's a parallel circuit here, in my view? This is concurrent. This is parallel. What would be powerful here? So this would be one way. But you know, this is 1, 2, 3. 3 concurrent, 3 parallel circuits. But you know, if I no, this is 3 concurrent circuits. But you know they will be in parallel. So this is 1 in 1. This is one parallel circuit. This is a disjoint group. So basically, you get like 3 sets of circuits here. So if you get like this one, basically I'm trying to remember the symbols now. So you get like an open switch, a switch is open. A switch is open. That's open, open, and then the switch is closed. That's closed. And you get the voltage, the symbols here. So you see this thing, the lines represent the geometry circuits of the topology state. So the concurrency model is this. So basically, let's start with the parallel model here. So you get here. So this model, this circuit has a uniform electricity. So if I take this the left side and go right, the electric will come out the other end and light the light bulb. So there's a light bulb here. This can be light. This can be light. So this has to be positively charged. In our worldview, this will be negatively charged. So in this circuit, in this quantum model of electric circuits, you have negative to positive, and that will go back to become positive to negative. So and this is the battery. The battery. With the switch, switch open. So switch the battery. So you get like that. Remember. So this is the battery. So you see this model? It's incomplete because you know we are doing about quantum systems now. So you see the charge goes this way from the battery. It goes up to the parallel circuit and comes down. So if I have the charge going at the unit I say it's going, the voltage has just to mention taking the voltage as well. But this circuit is now has a friction in it. Friction because of the medium it's in, which I call a chamber. So the chamber concept is very important to understand. So if I have like a copper wire, that is a copper conductor for electricity. But you know, I can't use copper for everything. Or gold. I can use gold, which is the best conductor. No, so is it gold or silver? I don't know right now. Yes, gold is the best conductor for electricity. It has the 100% system, but basically it's not the perfect system to do it either. Because for us, if I had to gold, I'll just do it. I believe gold. No, gold can't consider. I don't know. Basically, look at zinc, copper, nickel. Basically, zinc. You have to think of the best instrument. Gold is the best conductor of electricity. You get copper, which is the worst conductor, but it's cheaper. But this one I'm framing here, guys. I'm saying that gold is the best of the best. But also is it? So for example, if I want the best electric stream for this chamber, gold is fine. But gold is prone to degrade too, degradation. So that means that I can lose signal. Basically, I have the perfect signal, and no noise in this framework. But you know, it's not coherent because you know the gold material can degrade if this goes. If you ever have like a ounce of like dirt or things that conduct, or can start getting into the gold. So you get the perfect signal. And you get but you have the perfect signal. You have all signal and all noise. So you know, depending on the environment it's in. So that's what I'm really trying to prevent in this model. So if I have the perfect signal, I can send information when I need it in gold. But copper has the worst signal. What's the no signal? Because it's hard to conduct with copper. No signal. But it's stable. So you have to have something of this. All noise, no signal. Worst signal. But best. But no noise. But you know, it's hard to basically once you start it, you have to stop it. It's hard to stop it. The thing. Properly. This reminds me of my other problem I have to come to. So the perfect signal is fine, and the perfect noise is you get perfect signal. Which is my initiative? Oh, my time. Oh, my time. So you get a perfect signal. And no, no. This system, you have to get no signal. No signal. If you're using a quantum system, you get no signal, and sure no noise is in that signal. No, and you have to separate all the noises from the signal in your reality to their reality, because their noise can be in your signal too. Which is why we have a dual quantum model here. No signal, no noise. No noise, all noise, all signal. All signal. All signal and all noise. Which is why the thing exists for this model. It's kind of going to for 6 minutes here. So in this framework, it's fine. It's perfectly fine. Remove what basically you're trying to ensure that then your noise is not basically your noise is not the signal. Your noise is not the signal. It's not a signal, and vice versa. For polyglot systems, the polycore, etc. So you get no signal, no noise canicality. Canicality principle. You have to ensure that you have the medium is the interface you're communicating. Because their electron, their electron in our worldview is a positron. You know, our model for positron, and their model for positron, there's something that their model for positron is an electron in our world. Because electrical charge, a negative positive charge, when they have energy, when excited and have energy, and distribute across the system. So we see if you go to get something that's negative, but our concept of charge or force is not really universal to our system, based on the system. So we have to go. In their universe, they're positive and negative. Positive and negative. So if anything that's positive is just losing charge, It's antimatter. It's matter that don't it's a concept of anti. So we have an antimatter, anti-electron. So our electron, our electron is equal to their anti-electron, which is a positron. Our positron is their electron, is their anti-positron, which is their electron. Our proton is just natural. It doesn't have a charge. It doesn't have a charge or anything. It just be. It's stable. It's a stable isotope layer. Isotope just means it can have nucleus. Can have multiple nucleuses to define its mass. Isotope resolution is their unstable isotope canicality. You know, so what's stable for them is not stable for everyone else. Which you have to think of if you're just thinking about the RWB universe, the universe with everything's flipped, up and down, down is up, whatever you call it, and going there safely in your bubble, via the bridge I'm talking about. Thank you guys. Let me pause the video and I'll upload a new one. Today I'm going to be very busy. Thank you guys. Oh, stop.